Testing on YouTube. 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 All right. YouTube is working. And we're just waiting on X here. I think it's live on X as well. Spit out this gum. How's it going, Every Dream? Let's make sure it's working on X. Let's go. All right, it's working on X. Let's get started. Welcome everybody to another Hoopo stream. We're going to be looking at a couple different papers today in the audio and music generation space. So the main paper we're going to be looking at is this one here. This is called Flux That Plays Music, released on the 1st of September 2024. But we're also going to be kind of dipping into two other papers that are also relatively recent that I think give us a good overview of the land right now when it comes to audio generation. So this one's called Wav Tokenizer, right? Because that's a type of audio file. An efficient acoustic discrete codec tokenizer for audio language modeling on the 29th of August 2024. And then we're also going to be looking at this one here, LOOPY, Taming Audio-Driven Portrait Avatar with Long-Term Motion Dependency by the on 4th of December 2024. This one is not necessarily entirely audio. It's actually more about adding kind of these like lip sync animations to videos, but they condition their portrait avatar generation using a audio file, right? So they have to take raw audio and then compress it into some kind of thing that can then be used to condition their unit, which is actually doing the generation of the video frame. So really, we're mostly just going to be looking at the audio part of this model just to see how it compares to some of the pure audio research, which is what we're going to have here in Flux That Plays Music and Wav Tokenizer. So another thing to point out here, all three of these papers, right? You have ByteDance, Zhejiang University, you have Zhejiang University and Alibaba Group with a little bit of help from the Facebook AI research. And then you have Kunlun Inc., which is, I had to look it up, but it's basically some small Chinese startup. I don't know if it's actually small, but I have no sense of notion when it comes to the scale of these Chinese startups. But three different Chinese institutions here. And this one actually isn't even entirely coming from China. So the Flux That Plays Music, what they did, and you can actually look at the GitHub repo here. This is the GitHub repo for Flux Music. Is really this is just coming out of two already existing repos. So the code base is based on Flux and Audio LDM2 repos. So Flux is this here. Flux is a image generation diffusion model that is created by Black Forest Labs, and Black Forest Labs is actually Stability AI, basically. So Stability AI, they're the company behind Stable Diffusion, and they had a great team. They had their founder, Emad. Then there was some kind of internal drama, probably around lack of funding. You know, that's usually kind of where the internal drama starts. So they don't have enough money. The CEO, Emad Mustak, leaves. Then a bunch of the team members probably also realize it's not the best situation to be in. They leave, and then they create a new company called Black Forest Labs. So the team is basically just a bunch of ex-Stability AI people, and they release a new diffusion model, right? And this is actually the diffusion model that's behind X. So whenever you're in Grok and you're generating an image, you're actually using this diffusion model. But they also release the code for it, right? I don't think this has the training code. I think this is just the model and the inference. But then this random guy here from Kunlun Inc. basically took this diffusion model from Flux and turned it into a music generator. So rather than doing text to image, which is kind of the original use case of the Flux model, you're going to be doing text to music. And even though it's a different modality, it's actually not going to be significantly different, right? Because there's a trick that you can do with music or audio generation involving spectrograms, which we're going to get into, and it's basically a way of generating images that can be interpreted as audio. So we're going to start with the Flux paper, and that's going to be the stream today. We're getting super technical, right? It's going to be a lot of deep diving in here, so maybe if you're not super into audio, this might not be the stream for you, but if you're not necessarily into audio, you can also learn a lot by kind of reading these papers and thinking about problems in a different modality, right? That's kind of the way I approach these things. Is I think it's good to expand your content that you consume, your technical content. Try to consume technical content from different parts of the technical tree, and generally information and stuff that you learn in one thing will allow you to kind of generalize and get novel insights into different things. So you don't want to just read the same thing every time. So that's why I'm reading some audio generation stuff, even though I'm not really an audio generation guy. All right, so we're going to start off with the abstract here. This paper is a simple extension of a diffusion-based rectified flow transformer for text-to-music generation termed Flux Music, right? So Flux on music, it's diffusion-based generative model. There's a transformer in there, and the final ultimate thing it's doing is text-to-music, and we're going to go into what rectified flow is a little bit later. So it generates in the latent VAE space of a MEL spectrum. We're going to get into some of these words once we go actually into the paper. It's doing denoised patch prediction. There's multiple pre-trained text encoders, so the text that goes in is going in through multiple encoders. We've seen this trick before. We saw it on the SDXL paper, I think it was, where basically you feed your text into multiple text encoders. Each of those text encoders kind of gives you a slightly different semantic-y understanding of the text, and then that allows you to get kind of a better conditioning signal for whenever you're generating these MEL spectrograms. I don't know. Coarse textual information, time step embeddings, music patch sequences. I think we're going to get into that later. Data, code, and model weights are available publicly, so makes sense, right? If all of this work is based on the publicly available Flux repo, it would be kind of weird if they didn't publish the code, so they publish the code, but really it's largely just the Flux code. You can see it's almost the exact same kind of repo, right? All right. So we're going to skip through here in the introduction until they introduce the concept here of rectified flow, which is, I think, the first thing that we need to try to understand. So rectified flow is whenever data and noise are connected along a linear trajectory and offers improved theoretical properties. So data and noise connected along a linear trajectory. What exactly are we talking about there? So I have here a rectified flow blog post. I don't exactly know what this is, but it explains what rectified flow is largely doing. And the first thing you need to understand about rectified flow is you need to understand how diffusion models work, right? And diffusion models work by taking some sample in some space, and you're going to start off with effectively noise, right? And then you want to move to a different point in that space that represents an image, right? Such as this cat. So the way that you actually train this is you have a data set of cat images, and then you kind of over training, you will add noise and then you will learn to undo the noise that you added. And because you added the noise, you know exactly what the noise is, so you can remove it, and that gives you the perfect training kind of input and target, right? So that's how diffusion models are trained. They're basically trained to learn to remove noise that you're adding during training. And then during inference, you just start from noise, and then you just remove the noise conditioned on something, conditioned on text, conditioned on class, you know, if you want to go old school, and you'll get back the image. So the thing, though, is that you can think of this transition from noise into an image as a trajectory, right? So really imagine every single little pixel here, right? You have this pixel here. It starts off as maybe green. And then in the next step, the pixel gets a little bit more red, and then it gets maybe a little bit more red, and then maybe it gets a little bit more blue, and then it gets a little bit more yellow, and then it finally ends up in yellow, which is where you wanted it, right? So that trajectory that pixel took, right, where it went from blue to slightly red, then to slightly more red, then to slightly more yellow, then to more yellow than yellow, it's not a very straight trajectory, right? It's kind of like meandering around, and then before it gets to that final point. So fundamentally, what you're doing in a rectified flow diffusion model is you're rectifying that flow, right? You're basically saying, okay, I'm going to, rather than take this kind of like meandering path like you have here, right? Some of the ones down here, you see how it kind of like doesn't go to the final location, which is the image of the cat, from the noise. So the noise is this purple starting point, and the final image is the data is this red. So you're basically going there in one straight shot, right? And every single one of these time discretization steps, n equals 1, 2, 5, 10, 100, that's how many steps you're applying, right? So two-step rectified flow means you basically perform inference twice, but the path is kind of straight in between those, right? And it's not, so what I just explained to you is, I think, a good high-level summary, but it's not quite right? Because in reality, most of these diffusion models aren't operating in pixel space. So it's not that this individual pixel is becoming red and then blue and then green and then going to yellow, and instead you're going red to yellow. You're not actually, like, the trajectory isn't in pixel space. The trajectory is in some kind of latent space. So it's a little bit more difficult to understand, but the core concept of rectified flow that you need to kind of remember is that you're rectifying, or think rectangle, right? Straight lines. You're basically going straight from the noise to the data, and that allows you to go there faster and more efficiently. Okay. Does that mean we're restricting movement of trajectories with some equation? This is Yatharth asking a question. Not quite. Generally, the way this is done is you basically, it's like a kind of like a distillation, right? Where you're learning, you know where the endpoint is and you know where the start point is, so you can kind of say, okay, what if we went straight there, rather than what the model is currently doing. So I don't think it's an explicit constraint. I think it's more like you change the learning process and just try to get to that final point faster. There's variants of this as well, so it's not like there's a lot of different types of rectified flows, I guess what I'm saying. How's it going, Amelie, Sarah, and Every Dream? They're using a teacher model that uses many steps to train a student model that does this in fewer steps. Yeah, that's a good explanation, Every Dream. Okay, so that's rectified flow, right? Where your data, which is your images, and then your noise, which is what you're starting with, right? Some Gaussian noise, right? That black and white kind of snow, are connected along a linear trajectory. Okay. The other concept we need to think about here is the idea of transformer-based diffusion models that treat images as sequence of concatenated patches utilizing stacked transformer blocks for noise prediction. So what the transformer blocks are ultimately doing, right, is they have to predict this noise. So the transformer is getting this image right here, and then it's being told, tell me what the noise is, and it'll tell you what the noise is, and then we simply remove that noise and we end up here, right? So really what the transformer is predicting is the noise at every single step, and then we're just removing that noise. So that's why they're saying here the transformer is doing noise prediction, because it's predicting the noise. Treating images as sequences of concatenated patches, let's bring up a VIT again, VIT, Vision Transformer, right? So in a vision transformer, right, transformers are sequence models. They need a sequence of things. So in order to turn a two-dimensional image into a sequence of things, you turn it into these little patches, and then you feed the patches, usually with some kind of position embedding in there as well, to let the transformer know exactly where in the image that patch comes from. But in this case, right, the patches, denoised patch prediction, are patches of a MEL spectrogram. And I think, is that the next thing we should look at? Yeah, I think we should maybe look at that next. Actually, you know what? Let's go to that later. Let's go here. Flow matching is doing pretty well in the biochem AI space. Yeah, I think there's diffusion models that are used in biochem AI, right? Is the current state-of-the-art protein and molecule generative models diffusion-based? I don't actually know the answer to that question, but I could see it. Teacher trained on 1,000 time steps. Yeah, every dream definitely knows how to diffusion model. All right, let's get back into this paper. So, model architecture of Flux music. We use a frozen clap L and T5 XXL as text encoder. So you can see here that your text caption. So in this case, right, you're going to be generating audio from a text. So this is the text, for example, an experimental and free jazz psych folk tune with jazz influences from Europe. So you're taking that text right there. That's this caption, and then you're feeding it into these two frozen pre-trained text encoders. So I think T5 is from Google. I don't even know where clap L is, to be honest, but these are basically text encoders that take your text and turn it into like a little vector that represents the meaning of what's inside this text, right? So that's basically what's coming out of these, and they're not pushing gradients into these. So it's not like they necessarily want their loss function or their objective to slowly over time push gradients into these text encoders. They'd rather just use them as is, right? Somebody else took the time to train them, just leave them frozen, which just means you're not changing the weights, and then just use them. And they actually are a little bit more clever than that, where when they train this, let's see. They mention it somewhere over here, but basically during the course of training, they drop out the text encoders occasionally. So sometimes the model receives the caption, but this is all zeroed out. Sometimes this one is all zeroed out. And by having a dropout on the text encoders like that, your model becomes a little bit more robust to using one encoder or two encoders. So you could run inference with this with just one text encoder, and that would allow you to perform inference on this model with a smaller amount of memory and compute, right? Running both of these text encoders is going to take more memory, more time, more compute. So we saw this trick in the Stable Diffusion paper as well, right? Where you use dropout on the kind of ensembles of encoders so that you can optionally not use all of them if you're compute constrained. Okay. We saw this, so this is based on the recently open-sourced Flux model, right, which is coming from your Black Forest Labs. And in a way, you know, are they making the same mistake as Stability AI, right? So Stability AI, I think the main reason it failed is because they couldn't really get a business model going, right? It was an open-source company that basically gave away their model. And I'm a big fan of that because I'm a big fan of open source and kind of democratizing AI and giving people the power of AI. But the other side of that is that they have no moat, really, right? It's just everybody can kind of use their model, and it's not entirely clear like how they're going to make money. And I think that's part of why Stability AI failed. And here you have Flux kind of doing a similar strategy, right? Like they're basically just, hey, we're just going to release this model, and the result of that is that now some random Chinese company like these guys here, Kunlun, can use that model to do music generation. So now, you know, rather than keeping it, you know, it's kind of like a push and pull, right? Because why is Midjourney still around? Because they're so secretive, right? They don't give anybody else access, so people will continue to pay for exclusivity of their model. But I don't know. I wonder if Black Forest Labs has tried to improve their business model at all, or whether they're just going to take a whole new round of VC money and just dump it into open source, which I'm okay with. I'm okay with rich people getting a little bit less rich and all that money being used just effectively for the public good. But okay. Clap is clip for audio by Leon. Okay, Leon is the data set that was used for Stable Diffusion, so it's basically like a text encoder. AlphaFold 3 is a diffusion transformer. Okay. All right, so CLAP-L, I suppose that's the larger of the two. We are the first study to apply rectified flow transformers to text-to-music generation. I don't know if this is entirely true. I have like a sneaking suspicion. Like, rectified flow has been around long enough that like it feels to me like there's probably a couple random papers that have done this and they just didn't find them, but I don't know. I didn't find them either. So maybe this is the first paper to do this. Okay, we're going to skip through some of this crap here. Music compression. So to better represent music, each 10-second audio clip sampled at 16 kilohertz is first converted into 64 by 1024 Mel spectrogram, right? So you can see how this is now kind of an image, right? So fundamentally, the core thing they're going to be doing in this is they're going to be generating music, but generating music as images, right? So they're generating spectrograms, and then those spectrograms are can be converted into audio, or audio can be converted into this spectrogram. 64 Mel bins, hop length of 160, window length of 1024. So let's actually see what this is. So, and some of this might be a review. I think we've reviewed other audio papers before, and we've gone over Mel spectrograms and stuff like that. So if this is a little bit of a review, I apologize, but I think it's always good to kind of refresh, right? And this is what audio looks like, right? So the audio modality is really just a one-dimensional signal if you're using mono, a mono microphone or two, and it's really just a single point over a series of time, right? So here it says time, and what is the x-axis? It's samples. So if you're sampling audio at 44 kilohertz, that means you have 44,000 numbers to represent 1 second of audio. So those 44,000 numbers, which represent basically the point in this little noisy curve here, and this would be 1 second, right? So here they're sampling at 16,000 hertz or 16 kilohertz, and this is usually the sample frequency that you see. So even in, for example, Wav Tokenizer, they also use 16 kilohertz. They mention that many of these data sets are 16 kilohertz, and a lot of the evaluation metrics are also in 16 kilohertz. So I think this loopy also is 16 kilohertz. Where is it here? I think this is the one, WAV2VEC. Yeah, sampled at 16 kilohertz, 960 hours of livery speech on 16 kilohertz. And in here, they actually downsampled to 16 as well. Okay. But you have this, right? And that's kind of like a lot of numbers to represent 1 second of audio. So how can you break this down so that it's less numbers, right? How can you compress this signal? And we don't need to even use machine learning to do this. You can effectively use what's called a Fourier transform. And a Fourier transform is, I really like this GIF to explain what it is, but imagine you have this signal that you're trying to mimic, right? This square wave, right? So these dotted lines representing a square wave. One way that you could do it is you could say, okay, here's a specific frequency and amplitude. So the amplitude is the size of this circle, and then the frequency is how often it goes around. And you can see here with even just one term here, you can get this sine wave, which kind of closely approximates the square wave, but not quite. So if you want to go another level deeper, you could add another kind of term here. And in this one here, you can see the 3 theta and the fact that you're dividing it by 3. It's now, the amplitude is 1/3, so that's where this 3 is coming from. It's 1/3, but the frequency is also times 3. So you can see it's going around 3 times, and this one that goes there. And if you add these two together, you can now see that our approximation of this square wave signal is even better, right? So we've gone from 1 term, and we kind of half approximate it, to now 2 terms, and it's pretty close, right? And you can see how adding more and more terms gets us closer and closer to the actual signal, right? So you can effectively do the same thing with this type of audio signal, this raw audio. You can break it down into these numbers here, which is just the size of this circle and the frequency of that, right? And that's what you're doing when you're doing this Fourier transform. You're going from this random bullshit wavy thing that has 40,000 dots per second or 16,000 dots, and you're turning it into, okay, this specific frequency and this amplitude and this specific frequency and this amplitude, and if you add all of those together, you end up getting something that is very, very similar to our audio signal. All right, so here, for example, here's the amplitude at the different frequencies. So what the Fourier transform is telling you is like, okay, these specific frequencies with these audios, if you add all those together, you'll get the original wave back, right? Okay, now there's going to be 2 more steps. So this is good, but we can do better, and we're going to turn it into a spectrogram. So a spectrogram is you're going to have some magic numbers here, and the magic numbers are going to be this window length, the hop length, and the overall overlap length. Right, so here they tell you, for example, the window length of hop length of 160, window length of 1024. So those are the numbers right here, right? Window length, hop length. And you can think of these kind of like in a convnet, right? There's some size for the kernel. There's also the stride, like how fast is that kernel convolving across your image, right? So it's kind of analogous to the way convolution works in image encoding, where you have these kind of hard-coded numbers that you had to come up with, like the window length, top length, blah, blah, blah. Okay. But eventually, that allows you to turn this audio signal into this image, right? And now we have what we really want. We have what's called a spectrogram, which is, okay, here's 30 seconds of audio, and then here is basically the different frequency. So if it's 0, that means there's no frequency there for that. And then if it's, or I guess 0 to -80. So this is like, basically, you don't need any high frequency signal. You can just kind of create at every second the audio waveform by composing these things. And then we're going to take it one step further, which is we're going to take this spectrogram, and then rather than having this y-axis here, which is kind of arbitrary, we're going to have a y-axis that is based on the MEL scale, which is basically this hard-coded scale for humans. So the way that human hearing works is it's not perfectly kind of mathematical like this. There's a little bit of weirdness to it. For example, we are better at detecting differences in lower frequencies than higher frequencies. So there's this MEL scale, and then if you change the y-axis of that spectrogram into this MEL scale, now you have the final thing, right? And what is this thing? This is an image, right? So what we've effectively done is we've turned this signal here, this raw audio signal sampled at 40,000, into an image, right? And now that it's an image, we can just generate it with a diffusion model. And that's the TLDR of this paper, is they basically took the diffusion model that was released by the company that recently formed from all the Stability AI people, and they fine-tuned it on spectrograms in order to generate audio. Okay. Damn, you guys are popping off here. Flux withholds a lot. No trainer, no information on their data. The dev model is NC licensed. Pro is closed source. Yeah, that is one thing that I saw. So one of the things that I did in preparation for this stream is I cloned these repos, and then I put them into Cursor. And Cursor allows you to basically summarize the entire repository with something like Claude Sonnet 3.5. So I summarized the Flux repo. And it says blah, blah, blah. This is an image generation model developed by Black Forest Labs, built on latent rectified flow transformers, right? This rectified flow in the latent space. Flux is able to achieve 3 variants, Flux 1 Pro, Dev, and Schnell, but only the Schnell is open. I think the Dev has the non-commercial license, and then the Pro is only via API. So I guess that is a little bit different than what Stable Diffusion and Stability AI was doing. So they are maybe doing a little bit different of a business model here, but we'll see if it actually kind of works out for them. Utilizes PyTorch. Training scripts are not publicly available. Model utilities. Torch Vision, Pillow, Fast API, Streamlit, Grad.io, kind of your standard stuff here. Poetry for dependency management. Singleton pattern, which is pretty standard as well for anything PyTorch based. NSF, content detection, watermarking. Okay. And you compare that to Flux, it's basically the same thing. UNet, convolution, self-attention, time step embeddings. I think maybe that's the one thing that they kind of added here. So they talk about it here. They talk about time step embeddings. So maybe that's the one extra thing they added, but they also, I think, provide the training code. So, okay. Let's go back here. So they're taking audio, they're turning it into images, and then they're going to take those images and basically encode them with a VAE. Okay. Here are the different size models. So they release a couple different size models. You have a small one here and a giant one. Pretty standard. The input sequence consisting of the text and noised music gives you a noised latent music representation. You have the fine-grained text encoding. I think they coarse-grained is this one, and then fine-grained is this one. So it's the 2 different text encoders. That's the fine versus coarse. And they just concatenate them. The double stream block, we employed 2 distinct sets of weights for the text and music, effectively treating them as independent transformers that merge during the attention operator. Here they're talking about this double stream block. So one of these blocks has access to the actual kind of the sound or the music, right? And the text, right? So it has both the text and the sound. And it can do cross attention between those. But then the single stream block down here, it only has access to the text. So at some point you stop kind of giving it the audio and you're just giving it what's coming from the previous blocks. And that's the distinction here between double stream and single stream. But I don't know. In general, like super nuanced little things like that with the architecture, it's not worth kind of spending your limited meat memory to store these type of things because these things change a lot, right? The model architectures kind of like constantly phase in and out and are changing, so it's not super important here on those details. Here's the part that I was trying to find before. Multiple text encoders that have dropout on top during training, which allows you to then use any subset of text encoders during inference. Okay, so the data set that they're using is coming from the LP music caps, and they're going to be enriching the music captions produced by a fine-tuned language model. And again, this is very similar to the Stable Diffusion paper where they have this LP music caps data set, which is basically audio and text. But because the captions are going to be kind of small and shitty, they're going to use a model to effectively augment those captions, right? So rather than having just one sentence, it'll turn it into 10 sentences, and then those 10 sentences give you a richer text signal to condition your generation from, which then ultimately means that you'll be able to generate higher quality and more nuanced audio from it. So LP Music's caps is not a data set, sorry. LP Music caps is the music captioning model that they use to augment the captions for the data set that they actually train on, which is this one. Several data sets, audio set, music subset. What a terrible ass name for a data set. The million song data set, right? Magna Tag Tune, Free Music Archive, FMA, Music for All, And all of these are sampled at 16 kilohertz. But that to me is like one of the things that's a little bit, maybe they're leaving something on the table here, right? Because ultimately, I think they mention that you can, if you go to higher sampling, you could probably get higher quality, right? I don't know if it's this paper or the other paper where they do that. Okay. I don't know, but to me at least, I feel like we should be moving beyond this, right? It's like, it's kind of become a standard, but this is kind of like generating like 256 by 256 images, right? At some point, you're going to kind of max out on the quality that you can get in a small image resolution. And I think that when I'm reading these audio papers, they're all kind of stuck on this 16 kilohertz. And I wonder if you kind of went a little bit bigger, right? Maybe even to the point of 40 kilohertz, like you have here, right? Wouldn't that, sure, it's going to cost you more compute, but I feel like there's probably a new kind of standard for quality that you can achieve at 40 kilohertz versus all of these are just using 16. Okay. Damn, you guys are popping off here. I did a Refusion stream. They did the FFT thing. Yeah, probably. I forget, dude. I do so many streams that like all the content that I consume just instantly evaporates from my brain. It's, you know, it's not a great thing, but hopefully some of the stuff is sticking. But don't get discouraged if you're constantly forgetting what you're learning, which is pretty much what I've been doing for the past decade. They did not even bold strategy. Okay, you guys are talking about protein stuff. Okay, so let's go into this paper here, because this is another paper that was also popular that came out recently. And this one's a little bit more nitty-gritty, right? So in this one, they're generating songs from text by turning the audio into these images and then using a diffusion model to generate the images. This is a completely different type of paper. In this paper, they're more trying to improve the actual process of taking the audio and turning it into some kind of compressed representation of that audio, right? And that's what this paper is about. It's about this idea of this codec tokenizer, which compresses high-dimensional natural signals into a lower-dimensional discrete tokens, right? If you're ultimately going to be consuming this type of data with a transformer, you're going to need to turn this, right? This 40,000, you don't want to feed, like imagine if you had to feed every single 40,000 one, and like that wouldn't work, right? You want to turn it into a much lower dimensional discrete tokens so that your transformer can consume it. Okay, so they can compress 1 second of audio, which would normally be 24,000 numbers, into 40 to 75 tokens. Okay, that's a pretty strong compression. Generally, though, whenever you compress really hard like that, you're losing more information, right? So the more you try to compress something, generally the more lossy it is. So how good is it if you're compressing it this much? And it actually is quite good. We achieve these results by designing a broader vector quantization space, extended contextual windows, and improved attention networks, as well as introducing a powerful multi-scale discriminator and inverse Fourier transform structure. Okay, and another kind of big thing they're going to be talking about here is that they're going to be combining speech, audio, and music, because these audio tokenizers, they're not unusual. Pretty much everyone uses them. For example, here in the LOOPY paper, you can see a similar kind of audio tokenizer here. Not quite, right? This is a different model. This is Wav to Vec, but the whole point of this is that you're turning this audio into some compressed representation of that audio. And this Wav to Vec model here is actually this thing here, Wav to Vec from Facebook, and it's 960 hours of Libri speech, which is really just speech audio, right? And that's the distinction that this paper wants you to notice, is that a lot of these pre-existing audio encoders are kind of specific to one thing, right? So if you're doing this type of paper where you really only care about the mouth and the shape of the mouth and the audio that comes from speaking, right, then you can use an audio encoder that really only has been trained on audio data, right, like speech data. But if you wanted to do something like this, right, where you're generating music, you couldn't really use this audio encoder because it's just not, it hasn't seen any music. So in this paper, they're trying to introduce an audio encoder that works equally well on speech and music and audio, which I guess is maybe like sounds, you know, like maybe the sound of a dog barking is considered audio. But, okay, that's this paper. Discrete acoustic codec representations produced by a neural codec model. Ultimately, what they're doing is they're discretizing high-rate audio signals into a finite set of tokens, right? So you're taking this audio signal and you're turning it into a stream of tokens, which is a little bit different than what these guys are doing, right? Where they're turning it into an image. Okay. Utmos. What the fuck is Utmos? Utmos sounds kind of scary, but it's not scary at all. Utmos is just a metric. It's a kind of like a, let me see if I can find the explanation of it here. I should have like gone through this. K means, where's the Utmos? I thought I had the Utmos here. There we go, Utmos. So Utmos is an automated metric, which is basically some way of measuring performance that you don't need to have humans in the loop, right? You can perform it with code, right? It's called automatic mean opinion score, and Utmos is restricted to a 16 kilohertz sample rate. So that's not great, because it means to me that maybe part of the reason that all of these audio encoding and music generation papers are all stuck on this 16 kilohertz sampling is because even the metrics are limited to 16 kilohertz. So if we want to start having more high quality audio with a higher sample rate, we might even have to rehaul all the different metrics that we're using here. So I could see that being something that's preventing this entire research field from kind of moving into that higher sampling rate. But okay, Utmos represents reconstructed quality closer to human auditory perception. So this y-axis right here, the higher that number is, the better quality the audio is. So this is the shittiest model, and then this is the highest quality model in terms of just compressing the audio down and then uncompressing it. So like, how good is it at compressing that audio and then not losing the information, so that when you uncompress it, it goes back to being high quality, right? So this one here, it compresses it, but then when you uncompress it, it's shit. So you're kind of losing a lot of information here, versus obviously the Wav Tokenizer, which is this paper. You can see you're compressing it a lot because it's not a lot of tokens, right? But the quality is a lot higher. So it's a better type of compression. Kilobytes per second represents audio compression levels, and the size of the circles represents the number of discrete tokens per second. So why would more tokens be bad, right? So like, that's kind of usually more tokens is good, right? Like, you've kind of been taught to think like that, but the reason it's bad here is because ultimately you want this tokenizer to compress your audio into a sequence of, here it's just a vector, but you want it to compress it into a sequence of discrete tokens so that it can be used by a transformer, right? And those transformers have some limited context size, right? So if your audio tokenizer is producing 900 tokens for every second, you're very quickly going to fill up the context of a transformer. So if you can figure out how to take your audio and turn it into less tokens, then your transformer context will be a much larger chunk of time, right? So 10 seconds of audio at 75 tokens per second, you could fit all 10 seconds in the context of a transformer, versus 900 tokens per second. You might even not be able to fit, you might have to just do like 0.1 seconds inside the context window of a transformer, right? Depends on the transformer. There's a lot of little details there, but that's a reason why less tokens is actually a good thing when it comes to the tokenizer that you're using, or your model that's encoding or tokenizing the audio. Less tokens to represent each second means longer context and potentially faster compute. Okay. Unified modeling of various acoustic audio signals. Acoustic tokens offer the advantage of a reconstruction paradigm that can uniformly model speech, music, and audio. So what they're talking about here is that a lot of these models, like these ones here, like the Wav to Vec, that have been kind of exclusively trained on this speech data, what they're really outputting are what they call semantic tokens, right? So it's each little token that is coming out is representing the content of that audio, versus acoustic tokens, it's like the token is more representing the kind of sound itself, right? And by representing the sound itself, you can represent more possible different things, right? So imagine using something like Wav to Vec, right? Like maybe it has a very limited, like if you say the word hello, that's like one token that represents the meaning of the word hello, right? That's what's actually being output, is the word being said is hello, basically a little token that represents that. Versus something that is using acoustic tokens, there's a million different ways to say the word hello, and there might be different tokens to represent the different kind of intonations and the ways that you can say hello, right? So like it gives you a little bit more of a broader representational ability. That's an argument that they're making here for the acoustic tokens versus semantic tokens. Okay. And then they're talking about quantization here. So let me see if I can... DNA sequences, so you guys are still talking about DNA diffusion. Okay. Mainstream speech representations are divided into semantic and acoustic tokens. Semantic tokens often lack acoustic information, which means that you're going to be reconstructing audio poorly, and especially if you're trying to reconstruct not just speech, but things like music, right? That you're going to need pretty complicated acoustic tokens to represent like the sound of like some weird electronic synth in some EDM song, right? Like you're not going to have a semantic token that represents that or compresses that efficiently. Okay, another thing here, a robust acoustic tokenizer should at least maintain the encoder VQ decoder structure, which means that this codec model should primarily function as a tokenizer and detokenizer, right? So these are just different ways of basically saying you're taking some signal, you're compressing it, right? You're tokenizing it or encoding it, and then you're detokenizing it or decoding it, right? Which is just slightly different ways of saying taking something, compressing it, and then taking that compressed thing and then uncompressing it, right? But fundamentally what you want to do is take a bunch of information and turn it into a smaller amount of information that represents that larger amount of information. So specifically when they're talking about this encoder VQ decoder, right? I think we should bring up this right here, right? So we need to talk a little bit about what residual vector quantization is. And I actually really like this blog post. But here we go. I like this analogy here. In one dimension, residual vector quantization is the way we represent numbers using digits. Instead of creating 10,000 separate categories for each of the integers from 0 to 9,999, we use 4 code books for thousands, hundreds, tens, and ones, consisting of the tens digits 0 through 9, and then the tens place, then the hundreds place, and then the thousands place, and so on, right? So it's actually a much more efficient way of representing any number between 0 to 999 rather than having 10,000 possible discrete categories. So I think this is a good analogy for what exactly you're doing when you're doing residual vector quantization, right? Where you're quantizing the residual of the previous thing, and then the residual of the previous thing, and the residual of the previous thing. So you're kind of like going into the smaller and smaller details. We can represent real numbers to arbitrary precision by using more codebooks to include ever smaller residual vectors to the right of the decimal point. Okay, and VQVAE. Let's also look at the image here for VQVAE, because I think this is also an important image. Okay, this one. So here's a VQVAE in the original paper here, and you can see here the same kind of compression. So you have this encoder, decoder. The encoder's taking your image, using a convnet to compress it, and then taking that vector and then decompressing it back into the original image, and you want this image and this image to match. So in this little part right here, the image is now existing as this vector, and that vector, rather than storing all possible values for those vectors, right? You're going to have some limited possible values for those vectors, right? So you're going to have this code book, and the code book basically represents all the values for the vectors that you actually want to store, right? So it's kind of like your dictionary of vectors. And whenever you encode images, you're going to be doing this little k nearest neighbor stuff to kind of move these around and over time learn a code book. And if we go back to the residual vector quantization paper, right? Let's say you have, these are two-dimensional vectors, but obviously in our case, they're going to be much higher dimensional. But rather than kind of storing these at kind of infinite resolution, you can instead use KNN here, right, to create these kind of central area or centers. And that's actually how you initialize this, right? So they have a nice little explanation here. For example, short Fourier time. Here we go. The goal of Wav Tokenizer is to compress speech representation into the codebook space of a single quantizer, right? So they're not going to be using multiple quantizers, right? That's another thing. So for example here, each codebook, you could have another codebook inside of it. That's what they're showing you here, right? So you discretize your vector space, and then you discretize within that again, right? So you can get even higher and higher resolution. So you can see that when you're looking at residual vector quantization, depending on how many levels of quantization or how many of these code books you're using, you can get better and better estimates of the actual vector itself, right? So kind of the same way that in the original analogy here, when you're representing the integers from 0 to 9,999, right, that first digit is giving you a lot more information than the next digit and the next digit and the next digit. So there's this kind of like natural precision decrease as you go into higher and higher levels of quantization of the residual. And I think this is the best way to think about it, right? Is that you're basically, the first level gets you kind of close, and then the second level gets you closer, and the level after that gets you even closer and closer and closer. But the problem with doing that kind of stuff is that it kind of arbitrarily increases the complexity of your model, right? So when the number of quantizers exceeds 1, downstream models require additional design efforts, right? So it mentions here's a bunch of other audio encoders that people have come up with, and they have all these little tricks such as AR-NR structures, parallel generation, slanted autoregressive, global and local attention. With a single quantizer, speech modalities can be directly autoregressively embedded into large multimodal models. Basically, it simplifies by just having one quantizer, right? So far, a lot of the things in this paper are sounding pretty good, right? They're basically saying, okay, we're going to have less tokens than all the previous things. We're getting higher quality from these tokens. We're also going to be using a simpler strategy where you have less of this residual vector quantization. And fundamentally, it's still the same idea of just encoder, decoder, tokenizer, detokenizer. And the results are good. They achieve breakthroughs in compression, reconstruction quality, and semantic modeling, which means that even though they kind of simplified, they got a better result. So I think, honestly, this might be the best audio encoder right now, right? Better than Wav to Vec. So you can actually imagine redoing this loopy paper, but using this Wav tokenizer instead. And I bet you would probably work better in some situations. So it might not work as well as this one here, because this Wav to Vec here is kind of hard-coded or overfit to speech because it's been trained on so much speech. But I wonder if you had an image of a dog, you know, and now you had to basically get the dog to bark, right? This model here, because it's kind of been trained on a wider variance of different audios, it might be able to reproduce kind of sound effects better. So that's just kind of a random guess that I'm making right here, but that could be something, a new research direction is take one of these more generic audio encoders and use it for something like this, where you're using, or you're conditioning a diffusion model on it. Okay. Rethinking vector quantization. So the goal of Wav Tokenizer is to compress speech representations into the codebook space of a single quantizer. This allows for seamless serialization, avoiding the need for hierarchical design across channel dimensions. So this is the hierarchical design that they're talking about, right? You don't need to have multiple levels of quantization and different codebooks. They're just going to have one codebook, but they're going to expand the codebook space, right? So the codebook space, you can basically think of it like how many bricks are you cutting this into, right? So the more bricks you have, or the more of those little areas, more of those little individual entries in the code book, the more possible different things you can represent, right? So we were talking about maybe you want to have lots of different tokens that represent the different ways that you can say the word hello, you know? But at some point, you're not going to be using all of them, right? So at some point, if you have a code book that is absolutely massive, right? Like let's say you had 1,000,000 by 1,000,000, like a lot of those would be empty, right? The blue is like when you're actually sampling data, and then when you're quantizing it, you're basically just picking the nearest one here. So they did this nice experiment here where they look at the utilization rate, which is basically like how much of this codebook space is actually getting used. And they have a nice little table here where they show you the experiments that they ran on that. So, for example, see if I find it. Is it this one? NQ, number of quantizers, bandwidth. I thought they had that chart somewhere. It's this one. I think it's this one. Here we go. Utilization rate reflects the usage efficiency of the codebook, right? So you don't want to have a giant codebook if you're going to be using just a tiny part of it. So here, for example, they ablate this. So they want to compare what the difference is between different codebooks. So Wav Tokenizer small, all of these are the same size model. And here they're using a codebook with 16,000 possible values and a codebook with 1,000 possible values. So with 1,000 possible values, you can see a utilization rate of 100, which means that every single possible entry in that codebook is being used, right? And that's probably not good. You probably don't want 100% because it means that you're probably leaving some on the table. But once you went to 16,000, you got to 27% utilization rate, which means that a lot of those entries in your codebook kind of don't represent anything, right? They're just kind of some arbitrary point that maybe there's one audio that like is close to that or something like that, right? So they found this balance right here to be good, right? And I'm not even going to look at these because these are the automated metrics. So like, you know, to me it doesn't really mean anything that you're getting slightly worse utmos, you know, like that's not really a good metric or an intuitive metric to use, but I like the utilization rate as a way of determining what the optimal codebook size is. They use k-means clustering to initialize the codebook vectors. K-means clustering is effectively this process here, right? Where you have to decide where you're going to put those centers, which represent each of the entries in your codebook. And then over time, you basically move those centers. So you're looking at, okay, whenever I put images into here, like if the image is close to an existing entry in my codebook, then I'm going to move that entry a little bit, right? So the k-means, you start off with uniformly sampling, and then you're kind of like moving those little centers around, right? So you're kind of like, over time, what you're learning, when you're learning a code book, what you're really learning is like each of these little red circles that kind of like move around. Okay. Okay. We adjusted the number of cluster centers to 200, so they just start with 200. Improved decoder. Here we have the kind of Fourier transform, which we kind of saw before. To directly enhance the semantic modeling capability of the acoustic codec model, we introduce an attention model in the decoder. So the decoder is this part here, right? This is the decoder. It's the thing that's taking your compressed thing and then uncompressing it. And then the encoder is the thing that's taking your uncompressed thing and compressing it. Enhance information restructuring, reconstruction, and semantic modeling. And this is one of the big findings in this paper that they talk about, is this idea of doing it in 3 seconds rather than 1 second clips, right? And this goes all the way back to this argument that I was making here, right? Where because their decoder is a transformer and that transformer has a limited context, if your audio is represented by a lot of tokens, you're only going to be decoding small chunks of audio at a time, right? And what they're saying here is that most previous audio encoders, they're basically decoding 1 second at a time, right? But the problem with that is that 1 second clips may contain insufficient semantic information. So if you just have a 1 second clip in like a 4-hour podcast, it's very difficult to reconstruct a high quality version of that once that's been compressed. But by going to 3 seconds, you have an expanded contextual window, which allows you to pay attention to more of the surrounding information, which allows you to then generate a higher quality output, right? So kind of like a weird way of thinking about it is like, imagine if you had to reconstruct this entire image of the dog, but you only had like one patch versus if you had like 3 patches, right? Or 4 patches. You could reconstruct a higher quality version of that with a little bit more of the surrounding context. Here's a couple. So the losses are a little bit annoying here. So you can see they have like 1, 2, 3, 4 different losses here, each with a little hyperparameter. But you know, it's a little bit over-engineered, but that's kind of what you get. But they get good results, right? Like if you over-engineer your model and you don't get good results, that's not good at all, right? But if you get good results and you over-engineer your model, it's okay. It just means that you had, you know, you're doing a little bit of over-engineering, but the quality is there, right? So for these guys, even though it's a little bit, they have a lot of different losses here, I think that ultimately they get pretty much state-of-the-art results according to them. And a couple of these ideas, such as expanding the codebook space, training on a wider variance of audio, using less tokens, having less of these quantizers. I think there's a couple different things here that are good ideas. So overall, I think this is a pretty good paper. WAV Tokenizer Large was trained on approximately 80,000 hours of data. We can compare that to this one, 960 hours. So there's the comparison right there, 80,000 hours, right? So is that why it's better? Does all this other shit matter? Or is it really just the fact that it's trained on like 10x more, right? Because that could be it. Okay, Wav Tokenizer Medium trained around 5,000 hours, and Wav Tokenizer Small was trained around 585 hours. So Wav Tokenizer Small is really the only one that's comparable to the original Wav to Vec 2. Is this Wav to Vec 1? So they're not even using Wav to Vec 2? I'm looking at, this is the Loopy paper right now. We're using Wav to Vec. Is it Wav to Vec? Wave to Vec? WAV to Vec? Audio feature extraction. Concatenate the hidden states from each layer of the Wav to Vec network to obtain multi-scale audio features. They have this like kind of annoying like audio to latent crap, but really all they're doing is they're basically just using it to take that audio, turn it into some vector that represents that audio, and then use that to condition this diffusion unit to basically generate the mouths, I guess. I don't know if it's doing like masked generation. I don't know exactly how this paper works, to be honest. But we're only looking at it to compare to these audio papers. Okay, so these 80,000 hours of audio trained on 16 NVIDIA A800s, so no H100s. Throughout the entire training process, all input speech, music, and audio samples were resampled to 24 kilohertz. So you can see them trying to do it at a little bit of higher sampling frequency there. But just look at the number, look at this right here, right? Like, so DAC, hi-fi codec, like look at how many tokens this produces, right? Very high. It doesn't compress almost at all, and it uses a ton of tokens. So like this is almost like unusable, right? It's like, this is so much better. It compresses so much more and it uses way less tokens. Okay, what else can we look at here? We have the Utmos automated metric. I mean, obviously it's like beating all of these. So, you know, like here they're saying higher is better. So these arrows basically tell you higher is better. So a high Utmos score is good. But I don't really know how to judge this, right? I don't know what a score of 4 on Utmos versus a score of 1.5 on Utmos is. It's kind of hard to do that. So this paper does the good thing where they actually compare with people. Is it this one? No, unfortunately, it's not this one. It's this one. Okay. We're kind of bouncing around, so maybe it's a little bit confusing, but in this one, the Flux music paper, right, as we were saying, these evaluated metrics are not usually not good enough to tell you whether something's better or worse. So here they actually do a human evaluation, which is kind of the gold standard. You get people, actual humans, to listen to this music and then tell you if they prefer it compared to other ones. So Flux Music 3.35 compared to Audio LM 2.25. So you can see it's beating Audio LM2 and Music Gen, which is kind of interesting, right? And I think they actually say that it's not just like random people. They actually get experts. See, I think it's down here. Yeah, our evaluation team comprised individuals from diverse backgrounds, including professional music producers and novices. So it's not like they just got like a bunch of random people from the Amazon Mechanical Turk who like don't really give a shit and are just trying to get paid $4. So like they're just gonna click through the things as fast as possible. It sounds like they actually got some music producers, right? So this is like a human expert, someone who sits there all day and is basically constantly listening to sounds and like determining the quality of the sounds. And the music experts actually think that the Flux music is pretty good. So kind of crazy, right? But we're now, according to these two papers, right, and there's the caveat that I'm just reading a small subset of all possible papers, right? There's so many papers that ultimately, within the limited context of a human attention span, you're only going to read a small subset of those. But according to the small subset that I've read, it seems like the best text-to-music generation is actually using spectrograms and generating are using a image diffusion model to basically generate music like images, but then the best audio encoder is not doing this image stuff at all, right? So like I'd be super curious what would happen if you basically did text-to-music generation, but with something like this, the Wav Tokenizer. Would you get better than the image-based crap that they're doing here, or worse than the image-based crap, right? And what happens if you got you used human evaluation to determine that? You know, I think that's really the experiment I would like to see. And also, going another point here on these human evaluators, right? These are experts, but I feel like an expert professional music producer, like asking them to tell the difference between two 16 kilohertz audio samples, like, is that even like, you know what I'm saying? Like, what is they probably have a much higher quality ear, right? At some point, it's like, if you're going to be hiring professional audio people to determine the quality of your audio, you can probably use a higher sampling rate, right? I don't know, it still feels to me like they're leaving so much on the table by staying in this 16K hertz. Sheb with a question here. If they are generating music, I wonder why not consider normal features such as loops and keynotes and stuff like this that I assume easy to be detected or employed. Sheb, I don't know exactly what you're talking about, but you're probably talking about the representation. So the way that music producers generally make music is using these kind of MIDI representations. So something like this, right? Where you're basically, you have some discrete set of sounds, maybe like a piano keyboard, and then you're living more in the space of like, okay, this sound for this long. And there is some notion of that in this, right? Because ultimately, when you're looking at a spectrogram, right, it's kind of the same thing, right? You can see that there's, I can't tell, but if you were to look at like an EDM song or something that has like a house music kick, you know, you could probably see it. You would look down here in the low frequencies and you would see this repeating pattern of like bright, 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 which would represent that kick. All right, so very similar to like what you would do in like an actual music production situation where you would have like the drum and then you would pick when the drum goes at a certain pattern. So I think the model, right, this model that is consuming the entire song as an image and then generating the entire song as an image, where, well, actually it starts from noise and then it generates the song, but it knows, right, it kind of has this global context because it's looking at the entire song, right? And that's actually another important point here. That's another important point here, is that both of these papers, which are both claiming state-of-the-art encoder and this one's state-of-the-art music generation, both of them have very long context, right? So in this one here, each 10-second audio clip, so the entire 10-second audio clip is available to the model, right? So the context, kind of like the global, you can pay attention to all parts of that 10-second audio. And here, they also spent all this time talking about how like there's a huge unlock by going from 1 second context to a 10-second context, right? We explored the effect of extended contextual windows by incorporating an attention module. Using a 3-second audio contextual window further enhances the model's reconstruction quality. A 1-second window may contain insufficient information to be more affected by silence. So maybe the Audio LM2 and Music Gen and some of the previous music generation papers, they just had very small context lengths, which means that they aren't going to generate, there's kind of a limit to the quality that they can generate because they can't kind of pay attention to the whole song at once, right? But by generating in this MEL spectrogram space, you can pay attention to the whole song. So maybe both of these papers are kind of getting to the same point, which is this, like, the longer you make that context, the more the higher quality it's going to be. And getting to that long context means you're going to have to figure out some way of representing your audio in a much more compressed way. So one way you could do that is with the images, and a different way you could do that is by doing this codebook VQ stuff. You could build classifiers to detect things like the BPM and add that to the conditioning, but more work. Yeah, so what Everydream is saying here is that any model like this, right, you can imagine some kind of classifier. You train an image classifier that consumes this and then outputs some beats per minute, right? And then you can use that beats per minute to condition the diffusion model, and then that'll somehow give it more information. So it's like giving the information, conditioning explicitly on information is sometimes better than just kind of hoping that the information makes its way into the parts of the model that need to pay attention to it, right? And there's like a kind of a cool experiment that someone did similar to this, where I remember someone telling me that they trained a image classification model where they gave the answer away, right? So they were training an image classification model, but every single image, the pixel at the very bottom was basically the category of the image. So if you had 1,000 dog and cat images, right, the bottom pixel is either 1 if it's a cat or 0 if it's a dog, right? So you're basically giving the model the answer in the image. But even if you do that, the model is not capable of basically figuring it out, of realizing that the answer is in the single pixel in the bottom left corner, right? So that's a situation where if you gave the model the answer explicitly, right, like you condition the model on either a 0 or 1, and you put that higher up in the model, it would be able to learn to use that extra signal to get the answer right pretty much 100% of the time. But whenever the information is at the lowest level and it needs to bubble its way all the way to the top layers where the actual decision gets made, or the actual output of the model, then it can kind of get lost in that, especially if you're using some kind of convolution type situation where you're kind of convolving like you're doing in images, or like you're doing in audio with FFTs. Okay. The last hidden state of T5 is the fine-grained, and the pooler output of clap L is the coarse textual. So that's just kind of telling you what is here. So the last layer of this model is what they're using as the coarse text, and then the last layer, or the pool layer, where the pooling, this model will have some pooling at the end of it, which means some kind of aggregation of the layers underneath it. And that's what's being used here. Frichet audio distance, Kullback-Leibler divergence, and inception scores. These are kind of more automated evaluation metrics. So I mean, it's kind of hard to really tell. ASM and FMA datasets. Parameter counts of roughly 145 mil and 142 mil. So if we actually go here, we can compare directly to the model sizes here. I think they have this chart. Where's the model sizes chart? ¿Dónde está model size? Number of tokens. I want model size. I think they mentioned it. Maybe it's not in a chart, but it's just in a table. Yeah. I think they just mentioned it here. Let's find it. Let's find it. I mean, I don't know. It also doesn't necessarily matter because this is just an encoder, right? So like, it's not like you would use this by itself. You would use this in conjugation with a different model that actually does some kind of thing, right? So like, this tokenizer here would really only be used as part of the model. You would put it right here. $28 batch size, 200K training steps. Obviously, looking at an image isn't really enough to tell you whether this is high quality or not. But according to the humans, it's higher quality. It significantly enhances both the overall quality of the music and its alignment with the text input. Flux Music utilizes rectified flows transformers to predict the mouse spectra iteratively within a latent VAE space. So that's basically it, guys. Let's see if there's anything else left in this paper that we want to go over here. With the FFT, we had all the different losses. We have the different sizes here. What else? We had the Utmos score, the 16 kilohertz sample rate. Less tokens means more context. We had this codebook utilization to figure out the correct codebook size for this. And in conclusion, they introduced Wav Tokenizer, capable of quantizing 1 second of speech, music, and audio into 75 high-quality or 40 high-quality tokens. Compared to existing, it achieves comparable results and is way less tokens, right? So kind of the story here is that you get similar reconstruction quality to some of these bigger models that require more tokens to do stuff. Okay. And I think that's pretty much it. This paper, we were just looking at that. So that's the 3 papers. Let's see if there's any other stuff left over here. We were looking at the code base and then the 2 code bases that it is based off of, mainly just this Flux, Black's Forest Lab. We looked at rectified flow. We understood what mouse spectrograms are and how they are created from a audio signal. I love this GIF for understanding what a Fourier kind of approximation is really doing here, right? You're kind of iteratively getting closer and closer and closer to the real thing. Residual vector quantization, kind of what codebooks are, how you can have kind of multiple codebooks to kind of have more and finer resolution that allows you to get closer and closer. 1 codebook, 2 codebook, 3 codebook, right? Your infinite dimensional vector is almost perfectly represented by your discrete little code, which is also a vector. Wave to Vec 2. Here's a nice little GIF. HD, let's do HD. Can I do HD? Apparently all you're going to get is this potato quality, but here's the OG Wave to Vec. The original Wave to Vec. See, it's just a convnet. VITs, VQVAEs, okay. Let's go back. Let me read your questions, sip this water, and then we'll maybe do a little summary. They didn't do a comparison with refusion. Yeah. You never know with those type of comparisons whether sometimes people don't compare to things because it's annoying, right? So why did this guy compare to Audio LDM2? Because it's based on the Audio LDM2 repo, right? So it's annoying to have to, like, imagine having to run, like, you spend all this time training your Flux music model, and you finally get it to work, you do a bunch of ablation studies, and then you're like, okay, now I've spent all this time on this, now I need to do all my benchmarks for and evals for all these other models, and then you have to go to other repos and figure out how to run those, and it can be a huge pain, and sometimes it's not the exact same format, maybe it's a different sampling frequency, maybe the data set is different format, so every additional thing that you compare to is more work. So yeah, my guess is that they just didn't want to do the extra work to compare it to Refusion, but if you want to have a more conspiracy theory kind of mindset, it's because the Refusion is better. Because I've also seen that where sometimes people will compare to 4 things, and then their thing is better than 2 of them and then worse than another one, and they'll just get rid of that other one and just only include the things that it's better at. So sometimes it's a little bit sketchy when they only compare against a couple things and it's better than all those things, but sometimes it's just they just didn't have enough time, you know, especially something like this where it's like a startup, you know, like they have so much shit to do that they probably didn't have time to run and compare against like 14 other things. How hard is it to get into audio processing? Honestly, pretty hard. Like, I'm not an audio expert at all, and like audio processing and this kind of like signal processing like this, like this is not new at all, right? Like this is very, very old, you know? Like if you think about it, even in the like 1900s, people were like figuring out how to like put in, compress speech into like radio signals and stuff like that. So like this type of like signal processing stuff, there's decades and decades and decades of research and techniques and improvements on certain techniques, and then improvements on a different technique, and then another improvement, and then a guy does a PhD entirely on some version of the FFT. So like, you know, there's you probably need to spend like a decade to even get to the point where you really understand this stuff super well. But I also don't think it's super useful either, right? It's kind of like computer vision was like that too, right? Where there was like hundreds of these different little techniques and all of them were hand designed, and then you had like entire PhDs to just hand design another little part of another little metric. So like audio is kind of the same way too, right? Where it's like these things have been so over engineered and require so much expertise to add one extra little thing or make one little change that I don't think people are going to be making many changes to these. I think we're just going to rely on neural networks to just figure out the intermediate representations for us, rather than relying on some handcrafted intermediate representation that was designed by some human in the 1980s, right? So signal processing is probably going to go in that same kind of bucket, where eventually you're going to get closer and closer to the signal with the machine learning model, and the closer and closer you get to the signal, the less and less you need to rely on knowledge of this kind of shit like this. Let me see. Flux withholds a lot, no trainer. How's it going, Julien? Clap is clip for audio. I think we saw that. Okay, I think that's pretty much all the questions. I'm seeing a lot of VQ, VAE. Is it just me, or has it always been there? I think it's kind of always been there. You know, it's a pretty generic kind of idea, right? A robust acoustic tokenizer should at least maintain the original encoder VQ decoder structure. It's like anything else. It's a very easy way, right? Because the learning objective is very easy, right? You don't need labeled data set. You can just take any giant data set of shit in any modality that you want, and the VQ-VAE is a pretty efficient way of figuring out how to compress it, right? So it's kind of like modality agnostic. Obviously, this isn't modality agnostic, right? You're going to have to hand design the CNN and whatever you're doing here, but the concept of just like take this, compress it, and then have this code book of quantized possible values of that, and then use that to uncompress it, it's a useful idea. Tokenization, though, is a pain in the ass. Yeah, I think it's just there's a lot of different ways of doing it. You know, we're definitely at the part of scientific, of like machine learning research where there's still a lot of back and forth on these tokenizers. You know, it's like every new generation of models has a slightly different tokenizer. You have different tokenizers for different modalities. But I remember I think 2 weeks ago, we read a paper where they generated images by looking at the JPEG encoded version of the image. So like it generates an image by encoding the characters that are inside of a JPEG, right? So there's all kinds of different hard-coded ways to kind of take an image or an audio and turn it into basically zeros and ones so that your computer can store it as a file, right? And maybe rather than having all these kind of specialized different ways of encoding different modalities, maybe we end up in a world where the tokenization is happening literally at the lowest possible level, which is just zeros and ones, and it's generating audio by just generating zeros and ones one at a time, and it's generating images by generating zeros and ones one at a time, and it's generating videos by generating zeros and ones one at a time, and it's generating robot actions by generating. So it's like you can see how in the limit we might get to a point where every single modality is tokenized in the same way because it's tokenized as the lowest possible level, which is like bits, which is pretty crazy to think about, but like maybe we move in that direction. It's probably going to take like 10 years though. Okay. Is that it? Pretty much all the questions there. All right, let's do a little summary here. Then we'll give you guys back your Friday time. All right, here's a summary. So today's stream was called Flux Music, and the purpose of this stream was to go over some recent audio generation and audio encoding papers just to kind of see where the audio modality is at, right? So we reviewed, and I think it's important for me to say I'm not an audio expert. You know, I'm really not an expert in anything, you know, like I love getting technical and I love kind of learning about the details of these type of things. But, you know, at the end of the day, it's like I've never implemented a audio tokenizer, you know, so it's like don't necessarily take what I say like some kind of expert opinion here. I'm just interested in like understanding the low level details, even if I'm not necessarily an expert in these things. So we looked at 3 different papers. We started with this paper here, Flux That Plays Music, which is a paper by a Chinese startup where they basically took the latest stable diffusion model that's made by the new corporate entity that is kind of the smart people in open image generation, and they fine-tune it, or not fine-tune, I think they train it from scratch, but they basically train it. Maybe they fine-tune it? I'm not entirely sure. They may train it from scratch just because what they're ultimately doing is they're generating songs from text by generating images. So they basically generate an image. The image is specifically a MEL spectrogram, which is a pretty common way of representing a audio signal like this. This is the audio signal. You're kind of breaking it down using Fourier transforms, and then ultimately getting to an image, and then they're just training that latest rectified flow diffusion model to generate full songs. And it actually seems to work pretty well. So they got some expert humans, some professional music producers to sit there and listen to a bunch of these generated songs, and they actually prefer it over some of the existing works. So perhaps the current state-of-the-art music generation model, but hard to say. I certainly don't have the expertise to tell you whether it's the best or not, and it could be the case that I think the best audio generation models are probably closed source, so probably things like UDO or Suno.ai, right? They probably have something similar to this with more people putting more time into it, so maybe it's better. But another paper we looked at is this Wav Tokenizer, which is basically just kind of like an encoder decoder for audio that is better than existing encoder decoders. And there's a couple different tricks or a couple different key highlights of this paper. One is that they're capable of taking a audio signal and compressing it into less tokens, which means that you can have a bigger context for any model that consumes this, right? So if you have some kind of transformer model that's consuming audio, by using less tokens, right, you can have a longer duration of a clip, which allows you to then generate higher quality audio or kind of do more, right? Whatever your use case is, right? So for example, here, this was the Loopy paper. They're using a audio encoder here because they want to condition a unit that generates frames of a video of a person talking. But they're actually using a kind of an older encoder here. And this is the newer encoder. What else? They kind of simplify the architecture a little bit. So they have only one the number of quantizers. So they only have one quantizer, which means that technically they can get rid of all these kind of hierarchical model architecture requirements, right? So basically they can simplify the overall structure, which means it's going to run faster, it's easier to modify, it's easier to learn, it's easier to represent in code, I suppose. And then they also train on a much larger and much wider variety of audio. So by comparison, for example, the audio encoder that they're using in this Loopy is trained on 960 hours of Libri speech at 16 kilohertz. So pretty much exclusively speech data, versus this one here is trained on way more than that. We can go here. Trained on approximately 80,000 hours of data, including audio, music. You got Jamendo, Music DB. So like basically way bigger data set, simpler model, more compression, and bigger code book. So the way they describe it is, rather than kind of being semantic tokens, they're calling them audio tokens or acoustic tokens, because they can represent kind of acoustic concepts rather than just semantic concepts. Like a semantic concept would be like the word dog, right? But an acoustic concept would be more like the sound like d and og, right? So like there's just more there. So they expand this codebook space so that you have a lot of possible different values, and a lot of possible different values means that you can represent a richer distribution of signals. And if your distribution of signals is all possible audio, music, and speech, that's a lot of shit to try to compress. So you certainly need a large codebook. So less tokens, more codebook, more context, and you end up getting better results. But that's pretty much it, guys. That's the 3 papers. I think there's still, you know, like as an outsider looking into the audio domain space, it still feels like these are still kind of little hodgepodge systems, you know, like at the end of the day, we're talking about like something trained in, I think they have the actual hardware here, 16 A800s, 80,000 hours of data, you know. Here they're using the image generation model. So like, I feel like I'd love to see like the big professional version of this. And I'd love to see a version of this that uses a better sampling rate than 16,000. Like, come on. 16 kilohertz just does not seem high enough quality, right? Like, I want to hear crispy audio, and I feel like we need to get to 40,000 is usually, I think, the kind of top end that you can get. I think 44,000, right? 44,000 kilohertz, or 44 kilohertz dual channel audio, because I'm pretty sure this isn't even dual channel. This is single channel 16 kilohertz. So we still got a lot of progress to make. We still got bigger training budgets to use, and we still got more GPUs to burn, but I think we're getting there. because this stuff keeps getting better. That's pretty much it, guys. Thanks, Every Dream, Sarah, Sheb, MLCat, Yatharth, Amelie, Aries, Julien, and that's it. Thanks, guys, for hanging out. Hope you guys had a good time. If not, have a good weekend, and see you guys next week.